Hi guys, I'm Lauren Smith and I'm studying Theoretical Physics in Trinity. I'll be taking you through to 2019's high-level question 12. This long question has 4 separate parts, each worth 28 marks, so in the exam you would complete 2 parts in total to complete this long question. So, let's get started. Okay, so here's the first look at our question 12 here. It's looking like a pretty short question, mostly calculations, because of course this is a mechanics question. You're going to have that. We've got some definitions, we've got to draw a labeled diagram, that's later. But for our calculations questions, we've been given this handy diagram here, and it's always so helpful in the exam when they actually give us a diagram, so we don't have to draw it out ourselves, although I would recommend you, as we'll see in the calculations, to draw this diagram out again with a few extra labels, which will really help you with your calculations for the different values in mechanics. Okay, let's get started. First things first, we have to state the principal conservation of energy, okay? Now it just says to state, so all we have to do is state the definition itself, which is that energy cannot be created nor destroyed, but it can be converted from one form to another. And this definition will get you 3 marks. However, in the marking scheme, if you have a look at it, there was a little bit of a typo error made on the paper that year, and so anyone who even attempted this part here would get 3 marks. What typo error was it? I'm going to guess that it's because they put this part A here very close to this first part of the question instead of up at top, but that won't happen in most years, so always put down your definition. Before we move on to our calculations question, which is up next, I just want to draw your attention to page 55 of the Formula and Tables book, where we're going to be looking at the formulas for potential or gravitational energy and kinetic energy. Okay, so we're asked first to calculate the velocity of the mass when the ball is at position B. So originally the ball, and as you can see here, I've redrawn out the diagram as I said I would, with a few extra labels, which will help. The ball started off at this position here and ended up at position B, which is up here. Okay, so we're going to be looking at energy, which was the big hint that the first definition question gave us, to state the conservation of energy, which means that it's probably easiest to work with energy for your calculations questions. So we're going to be looking at the formulas mgh and a half mv squared, the first being the formula for potential energy as we saw, and the second being the formula for kinetic energy. If you state just one of these formula in your answer booklet, directly copied from the Formula and Tables book if you haven't learned them off by heart, then you'll get your first 3 marks. Okay, so the principle of conservation of energy states that the energy at the initial position or the starting point of a system is equal to the energy at the final point or the finishing position. So energy initial is equal to energy final. Okay, so what is the energy at the initial position? Well, at the original position, we're at maximum velocity, as the mass has gained no height as of yet, and therefore we have all kinetic energy and no potential energy, because the potential energy is governed by this height h value. So energy initial is just a half mvi squared, where vi is just going to be the initial speed. Now, what is the final energy? The final energy is going to have a little bit of kinetic and a little bit of potential energy, because as you can see here, the ball is still moving. It's going to have velocity because we are told to calculate the velocity of the mass, but it also has a little bit of height as well. It's gained a little bit of height on its journey up here. As you can see here in the diagram, I've denoted that height as height h. So therefore, in our final energy value, we have 2 terms, the potential energy term and the kinetic energy term. Now, this line of workings here will get you 3 marks. Okay, we can before we do anything else, we can simplify this formula down to the bare bones of it, because We weren't given the mass of the ball or whatever it is, but it is a common factor in all of the terms, so we can just divide that out there. I'm just going to strike everything off, just giving us this final simplified form. I should mention that this v here is the target variable which we're looking for. It's going to be the velocity of the mass of position B. Okay, so we know the initial velocity. We were told in the question that the initial velocity was equal to 4 meters per second. Now it says that it was the horizontal velocity. That means, as you can see in the diagram here and on the exam booklet, that there is no vertical velocity. You can see that clearly in the diagram. So therefore the horizontal velocity also equals the magnitude of the velocity, which is the velocity within this kinetic energy formula, just for reference. Going through the next variables in the formula, we need to find out what v is, but we know what g is. We're told at the end of the question, if you look there, that g is equal to 9.8 meters per second. However, we need to find out what h is. We can do that by just looking at the diagram here. We need to find out, in terms of the information we have, what h is. H is just simply the difference between the length of the string, as you can see here, which is just simply from this yellow dotted line I've shown here, down to the center of mass of the ball. Okay, so the length of the string is 0.8 meters, and the height h is just the difference between that and this side of the triangle right here. You can see here that I've just drawn in a right angle into the triangle. This side right here is the hypotenuse of the triangle, and it's actually in length equal to 0.8 meters, or the length of the string. We're told that the length of the string is 80 centimeters, but I've converted it into meters because you're supposed to work with SI units. So just do that conversion quickly. And to find out what the blue line is, we're going to use the trigonometric identity for cosine. We know that cosine of the angle, which is 35 degrees, is equal to the adjacent, which is the blue line. I'm going to call that, say, x, over the hypotenuse, which is 0.8. And we can get an expression for x as 0.8 times the cosine of 35. Okay, so we need to subtract this from 0.8 in order to get our value for h. So there we have a value for h is 0.8 minus 0.8 times the cosine of 35. And let's put this into our calculator and see what that value is. Remember, your calculator must be in degrees mode. If it's in radians mode, you will compute out the wrong answer. Just making you aware, we are working in degrees. So we have 0.8 minus 0.8 times the cosine of 35. Hit equals, and we get an approximate answer of 0.145. And obviously that's going to be in meters. Okay, so that's the height calculated. And for either calculating this answer here or showing this expression here that you've worked that out, you will get your next 3 marks. Now all we need to do is just substitute this into the formula. So we're looking for v. So I'm just going to rearrange this formula here to get v on its own. So now all we have to do is substitute everything in. And put it into our calculator. Remember that the height is now stored as an answer, so we can use this to our advantage when subbing everything in. So we have the square root of 4 squared minus 2 times 9.8 times answer, because it's stored, the value of h is stored in the answer, hitting that equal sign, and we have a full answer, which is around 3.62 meters per second. And I've rounded it there to 2 decimal places, so we have 3.63 meters per second. Of course, for your final answer, you're going to get a 3 marks, giving us 12 out of 12. Before we move on to our next calculations question, I want to draw your attention to page 51 of the Formula and Tables book, but this time we're going to be looking at the centripetal acceleration formula. A is equal to v squared over r. Okay, so next of all, we're going to have to calculate the ball's or the mass's centripetal acceleration at position B. Okay, so I've redrawn out the diagram here, but this time when the ball is just at position B, just to make everything that little bit clearer. And since we're looking for the centripetal acceleration, it's no harm to just jot the formula down before we look at any values. And why would I do that, you may ask? Well, you are going to actually pick up marks if you jot the formula down. So it's very important to jot all your formulas down in physics as per. Just copying it down from the Formula and Tables book will get you your first 3 marks. Okay, so what are V and R? We're going to need these in order to calculate the centripetal acceleration. Well, we know that V is the linear velocity at that specific point, which just happens to be the V we calculated in the previous question, which was 3.63 meters per second, which I'm going to write explicitly again in my calculations column. But what is R? R is the radius of the circular motion of the mass, which is just going to be the length of the string, which is R is just equal to 80 centimeters, but we're going to have to work with SI units here, so I'm going to convert it into meters, so it's 0.8 meters. Okay, so next we're going to substitute in all of our values into our formula and get the result. And the centripetal acceleration is equal to 3.63 squared over 0.8. And I would really encourage you to put down all of your workings in the exam, because in the marking scheme, specifically, you get 3 marks just for substituting your values into the formula. So if you just go from the formula to the answer, even if it's correct, you're going to lose 3 marks for no reason at all. So always leave every working on the piece of paper. So, what is this centripetal acceleration? Well, in fact, from our last question, we had as our final figure the velocity at position B. So naturally that's going to be stored as an answer in our calculator, very handily. Just putting in the answer squared, it's going to give us an accurate answer as possible. Remembering that the radius is 0.8, hitting equals, and we have a centripetal acceleration of roughly 16.455. And I think rounding to 1 decimal place is enough, so I'm just going to do that. And the centripetal acceleration I'm going to put down as my answer is 16.5 meters per second. Please don't forget your units. You will lose marks. And that will give you a final 3 marks. And I've just mentioned that the direction is indeed towards the centre. The centre being this point over here. And it is important to note the direction, even though you're not going to get any extra marks for it here, it is always helpful to put down the direction, because some years you could get a slightly harsher marking scheme for some questions. Okay, and finally, we are asked to draw a label diagram to show the forces acting on the mass when it's at position B. Okay, so of course, like in the previous question, we had to calculate the centripetal acceleration. Therefore, there's going to be a centripetal force. It's going to be acting towards the center of the orbit, pulling the mass inwards. And this is represented by the tension in the string. As you can see, I've denoted it with T, and it's going towards the center. It's very important to denote the direction and the force. We also have the gravitational force, i.e. the weight, and it's going to be acting downwards from the center of mass. Just to note, all forces acting on the mass will be from the center of mass and out in a certain direction, because in Newtonian physics, we're just going to consider practically everything as point particles, and the point where all the forces are acting is in that center of mass position. Now in the label diagram, I've denoted my tension as T and my weight as W. However, it is very, very handy to denote a key over, well, anywhere on the page, just to let the examiner know you know what the names of the forces are acting on the mass. I'd also explicitly label the string, the angle, the mass, which is at position B, because it specifically says a label diagram. And I just want to labour the point that you will lose marks if you do not label the diagram. Main thing is put in your forces. So where do you actually get your marks? You're going to get your marks for each individual force. 2 marks for the tension, 2 marks for the weight. Easy peasy. And we're done. Okay, so here is the first look at our question 12b, and we are told at the very beginning in this little blurb up here that a RAM, or a random access memory integrated chip, contains transistors in which there are doped semiconductors and capacitors. So this question is based on semiconductors and capacitors, and as you can see here, we're asked a couple of questions all about semiconductors, and then our 2 calculations questions are based on the capacitance of this capacitor in the RAM chip. So let's get started. And we are first asked, what is a semiconductor? So all we have to do here is just give a simple definition, in that a semiconductor is a substance whose resistivity is between that of a good conductor and a good insulator. If you ever want a tip in how to remember the definition for a semiconductor formula, all you need to do is look at the word semiconductor. There is a clue there, because a semiconductor we know is some sort of it's going to be a material, and it's semi, or half, a conductor, and then the other half naturally must be an insulator. So just stating this definition will get you 3 marks. And because we were talking about the RAM chips and how they were working with doped semiconductors, they're going to naturally ask us what is meant by doping a semiconductor. So basically, doping is the adding of small controlled amounts of certain impurities to a pure semiconductor to change its conductivity. And these certain impurities will be, say, atoms with a slightly different outer electron configuration than the pure semiconductor material, whatever atoms it may be. But a big thing is that these amounts are controlled so that we don't fully lose all of the properties of the semiconductor when we are trying to change its conductivity. Okay, so just stating that will get you 3 marks. And next we are asked, how can a semiconductor be doped so that its majority charge carriers are indeed electrons? So this impurity that we were talking about in the previous question, which is added to the semiconductor, must have more outer electrons or more free electrons available for conduction. If we have more outer electrons in this impurity, and if we add enough in controlled amounts, as a whole the material will have the majority charge carriers as electrons. For example, silicone is a semiconductor material, a pure semiconductor material. If we want to dope it so that the majority charge carriers are indeed electrons, we're going to add phosphorus. Now, phosphorus atoms are roughly the same size as silicone atoms, but they have an extra valence electron. Therefore, when they are covalently bonding with the silicone atoms in the semiconductor material, there's going to be an extra valence electron floating around in the material, and if you add enough of them to the silicone semiconductor material, you are going to get the majority charge carriers as electrons. Now, this particular type of doping makes the semiconductor into a so-called N-type semiconductor. Okay, so I've given a small definition and an example. However, either the example or the definition will get you your marks. So I'd always put an example in anyway. If your definition goes a little bit askew, you'll get marks for the example. And the total marks for this part is 3. Okay, and next we're asked, how can a semiconductor be doped so that its majority charge carriers are indeed holes? Now, holes are positive. They carry a positive charge on them. So we would have less outer electrons, or fewer outer electrons from the impurity, and therefore more holes are available for conduction. So that's the definition. And an example would be boron in the semiconductor of silicone. Okay, Again, like before, I've given an example and a definition. Either one will get you 3 marks. Now, when we have less outer electrons in this added impurity, like the boron, when this impurity or this which is an atom, covalently bonds with the atoms of the semiconductor material, there will be a vacancy or a gap in the lattice of the material, since this impurity has less electrons to covalently bond with the semiconductor material. For example, boron has 1 less outer electron in its outer shell than silicon, so therefore when it's covalently bonding, there's going to be an extra hole lying around. And if you had enough of them, we're going to have the majority charge carriers as holes. Okay, so moving on to the next part of our question, I just want to bring you back to the original question, where we are told that the capacitance of a capacitor in a RAM chip is roughly 90 femtofarads, and it operates at a voltage of 1.2 volts, and we are asked to calculate the energy stored in the capacitor when it's fully charged and the number of additional electrons that are on the negative plate of the capacitor as a result of it being fully charged. So let's begin. So before we begin our calculations, I just want to draw your attention to page 62 of the Formula and Tables book, where we're going to be looking at the energy stored in a capacitor formula. And also page 45, where we're going to be looking at the prefixes which appear in front of some of the SI units. Okay, so in particular today we're going to be looking at the femto, which is 10 to the power of minus 15. Okay, so we're asked, as we went through, the energy stored in the capacitor. So given this information and all of the formulas and bits and pieces from the Formula and Tables book, we can begin. So we know that the energy stored in the capacitor is equal to a half CV squared, where C is the capacitance and V is the voltage. Now we have both the capacitance and the voltage, so this formula is perfect for calculating the energy stored. Okay, so just by copying this formula down from the Formula and Tables book will get you your first 3 marks. So always, 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 and I will say this in every single video I put out there, put down any formula you think is relevant to the question, because more than likely you're going to get marks. Okay, now in the Formula and Tables book it says that W is equal to half CV squared. Now work is a form of energy. It has the same units of energy, the joule, which is the SI unit for energy, so therefore we can interchange these letters a bit. Okay, now we know that the capacitance is measured in femtofarads. However, this is not SI units. We need to just have it in farads, because the farad is a unit in terms of SI units, so therefore we can use it in this calculation. So femto, as we saw in the Formula and Tables book, is equal to 10 to the power of minus 15. So just substituting that in there, we have the capacitance as equal to 90 times 10 to the power of minus 15 farads. That's in SI units now. The voltage is 1.2 volts. That's also an SI unit, so we can now substitute everything into our formula. Now, substituting everything in is very, very important in physics. I'd always recommend you to substitute your values into your formula before you calculate the answer. Don't just skip from the formula directly to the answer, because you actually pick up marks in this particular question for substituting in your variables. So you'll get 3 marks for substituting into the formula. Even if you get the right answer for the energy stored in the capacitor, but you don't put down your workings, i.e. substituting it in, you will still lose 3 marks, because the examiner doesn't know where you've explicitly got that figure from. Have you actually converted the capacitance into SI units correctly, and so forth. And you'll see this as a pattern in the marking scheme. If you go through any question, guarantee you will be awarded marks for substituting it in. Okay, so keep that in mind. Enough of that. Let's calculate the energy. Whipping out our calculator. We have a half. I'm going to put it in decimal form instead of the fraction form I have in my answer booklet. It just makes everything a little bit easier, because it's easier to put in a decimal place than a fraction in a calculator. You're going to have to agree with me on that one. And because we're using scientific notation, I would always multiply 2 different values together using the bracket sign. It just makes your work in the calculator a lot neater, and you're less likely to make a calculator error. Okay, so squaring this 1.2 here, hitting that equal sign, and we get a value for our energy. Now, the calculator gave an answer to 3 significant figures. However, I'm going to give it to 2 significant figures, giving it to 6.5 times 10 to the minus 14 joules. If you look over here at the variables we've been given, they've all been given to 2 significant figures. Because if you look over here at the capacitance and the voltage is given to 2 significant figures. And we have 2 figures up here for the capacitance as well. So it makes sense that we keep the energy value in this format. Okay, that's just a tip, and that will get you 3 marks for your answer. You will lose marks if you don't remember the units. So before we move on to our final calculations part, I want to draw your attention again to page 62 of the formula tables book. We're going to be looking at the formula for capacitance. However, we're also going to need page 46, looking at the fundamental physics constants. But this time we'll be looking at the charge on an electron. And in the second part, like we went through there just a couple of minutes ago, we were asked to calculate the number of additional electrons that are on the negative plate of the capacitor as a result of it being fully charged. Okay, so we're given the capacitance, which is 90 femtofarads, or 90 times 10 to the minus 15 farads in SI units. And we're also given the voltage, which is 1.2 volts. Therefore, the number of additional electrons we can calculate from the accumulated charge on the negative plate. So we're going to have to calculate this accumulation of negative charge, which can be calculated from Q is equal to CV, which is the formula we saw earlier in the Formula Tables book. Because we have the capacitance, we have the voltage, we need the total charge. Okay. So again, like I said earlier, it's important to substitute in your values into the formula. Now, just copying the formula down from the Formula Tables book or substituting your values into the formula will get you your first 3 marks. So let's first calculate the accumulation of charge, which is just going to be 90 times 10 to the power of minus 15, again using brackets because we have scientific notation here, it's just a lot cleaner on the calculator, times 1.2 volts equals roughly 1.08 times 10 to the power of minus 13 coulombs. Please do not forget your units on the coulomb. It just helps you keep track as you're going through the solution. And this answer will get you 2 marks. Now, how can we jump from the accumulation of charge on the negative plate to the number of additional electrons on the plate? Well, so the number of additional electrons is equal to the total charge over the charge of 1 electron, and therefore we'll get the number of additional electrons from this. So we know that the charge of 1 electron is roughly 1.6 times 10 to the power of minus 19 coulombs. So dividing this by the total charge will give us the number of additional electrons on the plate. So let's put this into our calculator. Now, remember up here, I have the total charge as my answer. So on the calculator, it's going to be stored as an answer. So when you're putting it into this fraction form, we have the total charge, which is just going to be stored as the answer. You can type it out if you want, but you're less inclined to make mistakes this way. And this is over the charge on 1 electron. Be careful putting in that scientific notation. Hitting equals, we're going to get exactly 675,000 additional electrons on that plate as a result of that tiny charge we're given. Pretty amazing. And finally, this is our final answer that we were looking for, so we're going to get an additional 2 marks for this, completing our question. Okay, so here's the first look at our question 12 part C, and roughly this question is split into 3 parts. We've got one calculations question, which is worth 12 marks here, for which we will need the refractive index of water, which we are told is 1.33. So we better get started. And they tell us in the paper that as a light passes from water into air, note that water is a denser medium than air, because with respect to a vacuum, water has a higher refractive index than air. So when light passes from water into air, the critical angle may be exceeded and total internal reflection may occur. And we're asked to explain the underlined terms. The first underlined term is the critical angle, which I'm just going to simply give the definition here. It is when light travels from a denser to a rarer medium, which we have here. It's water goes to air. The angle of incidence whose corresponding angle of refraction is 90 degrees is the critical angle. And you can see that clearly in the diagram. If you're not much of a words person, diagrams explain definitions in physics sometimes even better than a direct verbal definition. So I've just given the diagram here. And as you can see here, for an angle of incidence going from the denser to the rarer medium, which is water goes to air, I've labelled the critical angle as C, the angle of incidence, and its corresponding angle of refraction is 90 degrees as well. Now, where do you get your marks? You get your marks for stating that it is an angle of incidence and that its corresponding angle of refraction is 90 degrees, giving a total of 6 marks. Okay, so next we have to explain total internal reflection. So all we need to do is give the definition, and it is when light is going from a denser to a rarer medium, which is water goes to air like before, and it strikes the second medium, as you can see here in the diagram, at the interface, with an angle of incidence that's greater than the critical angle. So this angle I here will be greater than C, and therefore it does not enter the second medium at all. It is all reflected back into the denser medium, which is water in this case. Stating that the angle of incidence must be greater than the critical angle will get you 3 marks. Okay, so we're going to move back to our question 12 part C, because we are given information which we will need in order to answer the following questions. We are told that a diver is 12 meters below the surface in a pool of water, underlining or highlighting all numerical values which we are given. Now, when this diver looks up, he can see a circular window of light on the surface of the water. This circular window of light, by the way, is also called Snell's window. With this information, we are subsequently asked to calculate something. But before we do that, I just want to draw your attention to a couple of pages in the Formula and Tables book. The first page is page 8, and we will be using the formula for the area of a circle or a disc. The second page in the Formula and Tables book, which I want to look at, is page 60. And we will be looking at the formula for refractive index, in particular, the one which includes use of the critical angle. Okay, so we're asked in this question to calculate the area of this disc of light. And the first thing we need to know when we're calculating the area of a disc or a circle is that we must calculate the radius. That is the only value within that area of a disc formula which we do not know, as we saw in that formula in the Formula and Tables book earlier. But how do we find the radius from the limited or seemingly limited information we were given in the question? Well, our best way of finding this information out is through the construction of a diagram. Diagrams are extremely useful in physics, and it would be my biggest tip ever if you were to draw a diagram when you're doing any type of calculations question in physics, because they can help you spot patterns, especially when you're looking at questions with angles, because you might have to use your sine, cos and tan rules, which use mathematics, or you might be able to spot alternate angles or opposite angles or whatever. And we will be using some of these concepts within this question. Okay, so what are the key points of this diagram here? How does it depict Snell's law and so forth? Well, I have my diver at the bottom of our pool, or 12 meters from the surface of the pool, the surface indicated by this teal line up here, and my purple blob is indeed our diver. And next, looking at 2 in particular light rays, which are quite important. The 2 light rays have an angle of incidence which is of 90 degrees. Like, this is going to be the maximum angle of incidence which we can have. And from the definition of the critical angle, this corresponding angle of refraction, which you can see down here, is going to be the critical angle. It also is the same on the other side. It's this kind of a symmetrical diagram here. And therefore we have Snell's window. By the way, any other angle of incidence which is less than 90 degrees corresponds to an angle of refraction, which is within this circle of light here, i.e. within this kind of range here. However, how can we determine the radius of the disk from this? Well, we can spot a connection between the critical angle and these two angles in here. Namely, through alternate angles, we can see that both of these angles in here are indeed the critical angle. The radius of the circle is given by this length here, or the same length on the other side of the other triangle. And since we know one side of the triangle, which is the 12 meters, and we can find out what the critical angle is because we were given the refractive index of the water, we can, in short, find out the radius of the disk of light, and therefore we can calculate the area. So let's get on with this calculation. We are told that the refractive index of the water, or as light rays are going from air to water, is 1.33. This connects to the critical angle in the formula n, which is the refractive index, is equal to 1 over sine c, where c here is the critical angle and corresponds to our theta sub c, which I showed in my diagram. Therefore, we can just substitute the value of n into the formula, rearrange our formula, and in short, we can find out what the critical angle is. Okay, so make sure you remember what mode your calculator is if you're calculating anything to do with angles, whether it be in degrees or radians. In this case, I have my calculator in degrees. Normally, they prefer to have you use degrees in the physics exam, but it really, at the end of the day, doesn't matter all that too much. Okay, so we have the critical angle is equal to sine inverse of 1 over 1.33, hitting that equal sign, and we get an angle of 48.75, or we can round it to 1 decimal place, which gives us a critical angle of 48.8 degrees here. Specify whether you're using degrees or radians again. Always put down an answer. Try not to put down the whole 12 or so decimal places here, but in order to keep your answer as accurate as possible, I'd either store this long decimal for the critical angle within the calculator or keep it up on screen, because just to make your answer as accurate as possible as you go along to reduce any rounding errors for your final answer. Okay, so you do pick up marks here if you either mention this formula here, this formula line here, or calculate the correct critical angle. You will get your first 3 marks. By the way, you do not have to include all of these in your rough work. You'll only need one of them to get those 3 marks. However, I would put down every single piece of work that you can possibly imagine onto your exam paper. Okay, so now we have the critical angle. How do we figure out the radius? Okay, so taking the triangle, which I had in my first diagram, back down here to try and look at the relation between the critical angle and the radius, and which trigonometric identity we use in order to calculate the radius. We have the angle, which is c, the critical angle, and we have the distance d, which is 12 meters. The distance d corresponds to the adjacent of the triangle, and c obviously corresponds to the angle. Since r, the radius, is the opposite of the triangle, we conclude we must use the trigonometric identity tan. So tan of the angle is equal to the radius over the distance between the surface and the diver. Now substituting in our values and then rearranging our values so we get the target variable, which is the radius of the circle of light on one side on its own and all other numbers on the other side, we can now calculate the radius. Okay, so having the calculator up again, this is what I mean about keeping this long decimal answer of the critical angle up on screen, because this is going to be stored as an answer. Remembering you must keep your calculator in the same angle mode as before, i.e. in degrees mode. We have 12 times the tan of the angle, which is just stored as an answer here, and we get our answer for the radius, which is roughly 13.7 meters. Rounding all these little answers here on your exam script, but keeping them in full decimal value in your calculator. Now, you do pick up marks here if you either put down this trigonometric identity for tan here, or put down this substitution in here and this kind of rearrangement here, or if you calculate the correct radius, you'll get your second 3 marks. Now, let's calculate the area. The area of a circle is given by pi r squared, where r is the radius. We know that the radius is 13.7 meters. Let's calculate the area. Pi times the answer squared, because we're keeping this radius answer we calculated before stored as an answer in our calculator, just to give the full answer, which is not going to be swayed by rounding errors. Hitting that equal sign, we are going to get this as our area. Given that area is by convention rounded to the nearest full figure, I'm going to do the exact same here and tidy this answer up so that the area is equal to 590 meters squared. Please do not forget your units. You will lose marks if you forget them. Okay, you get 3 marks for putting down the area of a circle formula and another 3 marks for the correct answer. Okay, so for the final part, we're asked to use a label diagram. So please label it, because you will lose marks, to explain why the diver does not appear to be at a depth of 12 meters when viewed by an observer outside the pool. And the answer is as follows. We know that the refractive index of a medium is equal to the real depth over the apparent depth of when you're viewing an image. That's in your theory. And since the refractive index of air is less than the refractive index of water, we know that the real depth of the position of the diver is going to be greater than the apparent depth of the diver, as you can see in the diagram here. So we have that the light rays are going from the apparent intersection of the light rays to the eye, where they do not appear to bend, when in reality they do, as you can see from the actual position of the diver, and therefore it forms an image. So it is the image if there were no water there or no refraction. Okay, so I've drawn in a load of labels, as you should, because you will lose marks. I always use this to stress my point, because you can lose a lot of marks for just missing out on the little nitty-gritty details like that. And where do you get your marks? You get your marks for the correct refracted ray, which should be down here, and the correct apparent ray, or the correct position of the image, which is given up here, will get you 3 marks, giving 7 out of 7. Okay, so for those of you doing this particle physics question, here's the first look at question 12D part 1. Okay, so just a little bit about it. We're told that the new Swiss 200 franc note honours proton-proton collisions in the Large Hadron Collider at CERN. I'm just taking a note that it says proton-proton collisions, and we are just then asked a couple of questions regarding this. Okay, so before we move on to the first question, I want to draw your attention to page 48 of the Form and Tables book, and I'm going to be looking at the 2 classes of particles, mesons and baryons, in particular noting the particles within these 2 classes. Okay, so we are told that there are 2 families of hadrons, and we are to name them and distinguish between them. Okay, so the 2 families of the hadrons are the baryons and the mesons. Stating this correctly will get you 3 marks. And how do we distinguish between these 2 families? Well, the particles of the baryons are composed of 3 quarks, and the particles that make up the mesons are composed of a quark and an antiquark. Stating this will get you 3 marks. Okay, so why did I mention the Form and Tables book just a couple of seconds ago? Well, the Form and Tables book can provide you with many hints in the exam. Treat it as if it's going to be your best friend, because honestly, it can be a lifesaver, especially for particle physics. So the information throughout this question 12 part D part I mentions protons and pions. And if you go to this page 48, under the baryons, proton is one of the particles in the baryon section, and the pion is a meson particle. Therefore, these 2 families, out of the 3 presented in the Form and Tables book, are the most likely candidates for the 2 families within the hadrons. So if you're ever stuck, Form and Tables book is great for these sort of questions. Okay, so just bringing us back to the original question, we're given a little bit more information. So we're told that 2 protons, each with a velocity of 0.9 times c, and c is the speed of light in this question. and they are traveling in opposite directions. And these two protons collide, and therefore in the aftermath a neutral pion and the two protons remain after the collision. And we're asked a couple of questions on this. Okay, so we are told that the single pion produced in the collision must be neutral, and we're asked, okay, explain why this is the case. And the answer is that due to the conservation of charge within physics, there must be an equal quantities of charge with the same sign, obviously, on the charges before and after the collision in this system. Okay, so we had two protons before the collision, so overall they'd give us a positive charge equating in value to the charge on a proton. And we have two protons after the collision plus an extra particle. So we need to have that same amount of charge after the collision as before, and this can only be the case if this pion has no charge or it is electrically neutral. Explaining this will get you 3 marks. Okay, so before we move on to the calculation, as part of this question, I want to draw your attention to a couple of pages in the Form and Tables book. The first one being page 48, like we saw earlier, but this time we will be looking at the mass of a neutral pi meson. Next, we have page 46, where we're going to need the electron mass. Another page we'll need is page 55. We'll need the two formulae for the kinetic energy and for the mass energy equivalence formula as well. And finally, going back to more fundamental physics constants, we're going to go to page 47 this time, where we're going to be looking at the proton mass and the speed of light in a vacuum. And what are we asked to calculate? Well, we're asked to calculate the total kinetic energy of the 3 particles after the collision. Note this is after the collision. So we had in the collision that before we had 2 protons traveling at equal velocities in opposite directions. They crash into each other and they are still intact after the collision. However, the energy from this collision also creates a neutral pi meson particle. Okay, so we're going to need the kinetic energy formula because it's asking us to calculate the total kinetic energy. And this formula for kinetic energy is a half mv squared, where m is the mass of said particle and v is the velocity of that particle. Just for putting this formula down, you'll get 3 marks. As we saw, it isn't freely available in the Form and Tables book, so not putting it down would be kind of a waste of marks. You don't even have to memorize it. All you need to do is copy it down. Because there is a creation of a particle within this collision, we're going to need the mass energy equivalence formula too, namely E is equal to mc squared. So the change in energy within this collision is going to be equal to the mass of the said particle created times the speed of light squared. Now we have that the kinetic energy after the collision is equal to the kinetic energy before the collision less the energy change in order to create that new particle. Okay? So that's the kinetic energy of the particles after the collision, because the particles, well, the protons will be at a lower speed than before, because some of that energy is transferred into making the mass of the pion. Okay, so let's calculate the energy before the collision. And that's just going to be 2 times the kinetic energy of 1 proton, because we have 2 protons. And therefore, when you substitute all in your values, and by the way, I'm going to give all of my answers here on my values to 4 decimal places, because we're going to be working with very small quantities of energy. So if you use more decimal places, you're going to get a higher accuracy. Normally in calculations in physics, you don't have to go to this high degree of accuracy, but due to the very, very small factors and changes of energy, it's better to give more decimal places. Okay, so let's put this all into our calculator up here. So here we have the mass of the proton. I'm going to multiply this using brackets, being very, very careful, because there's going to be a lot of scientific notation in here. We also got a square, which we need to take into account. And here I'm just typing in the value for the speed of light squared. Normally, the speed of light, we approximate it to 3 times 10 to the power of 8 meters per second. However, since I'm giving all my other answers to 4 decimal places, I decided I'd do the same for the speed of light as well, to keep everything consistent. Okay, so let's hit that equals button. And this is the kinetic energy before the collision. Again, keeping this answer to 4 decimal places. again keeping that consistency. And if you get this answer, or you write down the correct substitution into the formula, you're going to get your next 3 marks. Okay, so now we have to calculate the energy after the collision, and that's the energy before the collision minus the mass of a pion times the speed of light in a vacuum squared. Now, what's the mass of a neutral pion? Well, we're told in the Formula and Tables book that it's 264 times the mass of the electron. Okay, so we have here the mass of an electron, and it's being multiplied by 264 because, as I said before, the mass of a pion is 264 times the mass of an electron. Again, having the speed of light all squared and keeping all of our values to 4 decimal places or 5 significant figures. All we need to do is put this into our calculator and calculate the total kinetic energy. Before I do that, however, I want to point out that if you write down E equals mc squared, this formula for the kinetic energy after the collision, or that same formula but with all the values substituted in it, you're going to get your next 3 marks. Okay, so without further ado, let's just put this all into our calculator. Okay, so remember in the calculator up here, we have the value for the energy, the kinetic energy before the collision. So this is going to be stored as an answer. So I'm just going to put that in here. So we've got the kinetic energy before the collision minus 264 times the mass of an electron, all times the speed of light squared, hitting that equal sign, and we get this as the value of our kinetic energy after the collision, which is roughly 1 times 10 to the power of minus 10 joules, because we're working with energy, therefore that's the unit we're going to be working with. Do not forget your units, you will lose marks if you do. And that answer will get you your final 3 marks. Ending this calculations question. Okay, so bringing us back to the original question for the final couple of parts of this question. We are told that this Large Hadron Collider is indeed a circular accelerator. And we are asked, how are the protons maintained in this circular motion? The answer is as follows. The protons are maintained in circular motion with magnetic fields, and these magnetic fields provide a centripetal force. Because magnetic fields provide a magnetic force on charged particles. And if you remember from studying magnetism, this means that the particles will also experience from this a centripetal force. Explaining this will get you 3 marks. And for the final part of this question, we have to state the principal advantage of a circular accelerator over a linear accelerator. And there are 3 ways you can express this principal advantage. The first one I have is a greater energy can be created. The second one, the design of the accelerator is more compact. And the third, there is a longer path available for the particles. Looking at the second option, the design of the accelerator is more compact. This compactness means that something too massive to maybe build on Earth is actually not required to give the particles such large amount of energy. We can just do this by making a circular accelerator. Now, the infinitely long path, which is available for the particles, as I expressed in the third point, this is created by making the particles go round in circles, and this allows us to have this compact design as we saw in our second point, and therefore it gives the particles such large amounts of energy. Writing any of these 3 down will get you 4 marks. Okay, so for those of you doing applied electricity, you're going to answer D part 2 if you're going to tackle part D in this question 12. Okay, so here's part 2, and we are looking at a question which is roughly split into 2 parts. The first one out of 9 marks, the second one out of 19 marks. So we better get going with it. Okay, before we move on to the first question, I just want to draw your attention to page 76 of the Formula and Tables book. In particular, we're going to be looking at the circuit symbol for the MP junction transistor over here. Okay, so first of all, we're asked to draw the symbol for a transistor and a diagram of its structure. Okay, so over to the left, we have the symbol for a transistor, okay, which we just saw in the Formula and Tables book. So you don't even have to remember the symbol for a transistor. All you need to do is copy it from the Formula and Tables book and know where to find it in the Formula and Tables book, which is ideal. However, you need to be able to identify within this symbol the different parts. It doesn't ask specifically to label the parts in the symbol, but I've done it anyway, just so it's clearer when we're going to look at the corresponding diagram of its structure over here. So the diagram of its structure is over to the right. We're going to be mainly looking at NPN transistors. So we have the base over here, and we have the NPN part of the transistor in the middle, and then in the upward direction we've got the collector, and the downward direction we also have the emitter as well. The three main parts being the base, the collector, and the emitter. Okay, so it's your standard diagram, and you're going to get 3 marks for drawing the correct symbol, 3 marks for the correct diagram, and then 3 marks for all of the labels on it. Remember, labeling this diagram is key, and we're pretty much done this part of the question. Okay, so we are told that transistors and resistors can be used to construct voltage amplifier circuits. So we have that we need both transistors and resistors for voltage amplifier circuits, and we're asked to draw a circuit diagram of this voltage amplifier circuit. And here it is, I have it here. The arrangement. Okay, so the key features here, obviously the key features as pointed out to us in this question are going to be the transistors and the resistors. So you're going to get 3 marks for including your transistor, your bias resistor over here, or sub B as I indicated on the diagram, and the load resistor here, or sub L. So that's just mentioning these 3 in the circuit diagram will get you 3 marks. And if you have the correct arrangement, which I have here, you should be learning this pretty much as part of the content, you will get your next 3 marks. Okay, so in particular, when you're drawing circuit diagrams, whether you're studying applied physics or you are looking at electronics in Leaving Cert, look at the pages 72 to 78 of the Formula and Tables book, because you will be given all the circuit symbols, and they are very, very handy to jog your memory or just to give you a rough guide when doing circuit diagrams. Okay, so still on the topic of this voltage amplifier circuit, we are asked with respect to the diagram in the previous question to label the bias, the load resistor, and the input and output voltages. Okay, so I've just copied the diagram here. Normally you wouldn't have to draw the diagram out twice in your solution booklet in the exam. Just remember to label them explicitly, okay, and make sure it's very, very clear. Okay, so you will get your marks. This is the standard diagram you're going to have to learn of, but let's look at the key features. The bias resistor and the load resistor are here and here, and they must be in these positions. So the bias resistor is roughly connected with respect to the base of the transistor and near the input voltage, as we have over here. We have that the load resistor label, it is attached to with respect to the output voltage up here, and also the collector part of the transistor. So labeling these correctly will get you your first 3 marks. Okay, so the next 3 marks goes for having the input voltage in the correct place, and it must be between the base of the transistor here and the emitter, which is down here. Okay, and that will get you 3 marks. And for your final 3 marks in this question, you have to indicate that the output voltage can be measured between the collector and the emitter for this below one here, or the output voltage can be measured as the voltage across the load resistor. That will get you 3 marks, giving us 9 for these labels in the diagram. Okay, moving on, we're still talking about the voltage amplifier circuit, which means that it's very, very important in applied physics, your course, so I would learn it very, very well. Okay, so what is the purpose of the bias resistor, which we saw in the diagram earlier? Basically, strict definition, the bias resistor ensures the base emitter junction is always in forward bias. Remember, the bias resistor is connected to the base of the transistor, as we saw in the diagram previously. Okay, this correct statement will get you 2 marks. And finally, we're asked, what is the purpose of the load resistor? Well, The load resistor converts changes in the collector current to changes in the voltage across the load. And remember, the voltage across the load resistor is indeed the output voltage, as we saw earlier, and the collector current runs through this load resistor because the collector current is the current that comes from the collector of the transistor. If you don't believe me, check out the diagram which we just drew earlier. And this correct statement will get you 2 marks. So key thing here is when you're learning your voltage amplifier circuit diagrams, obviously know the configuration of the circuit, know the key circuit symbols within the circuit, what their function and purpose is, and where they are located in the circuit. And if you want to go in for a little bit extra detail, try and look as why they are there. And that's our question done.